Okay, let's solve the inequality negative 2x cubed minus 6x squared plus 12x plus 16 is less than or equal to 0. First thing you actually want to do here to solve this inequality, we need to factor this fully. So to factor this fully, we know that this is a third degree polynomial. It's a cubic equation, and in order to do this, you have to actually employ remainder theorem and factor theorem. Okay, so to kind of do this, you're going to have to do a little bit of guess and check. What will help you out with this is the potential factors of our cubic expression, which is like negative 2x cubed minus 6x squared plus 12x plus 16. The potential factors is plus minus the factors of the constant, which are 1, 2, 4, 8, and 16. So they're factors of 16, over plus minus the factors of the leading coefficient, which are 1 and 2. Okay, and our potential factors, and we say they are potential because it doesn't mean that all of these are factors, but some of these or one of these will be a factor. So some of the potential factors can be 1, 2, 4, 8, and 16. And also 1/2, so 1 divided by 2, 2 divided by 2, which is 1, 4 divided by 2, which is 2, 8 divided by 2, which is 4, 16 divided by 2, which is 8. So we also have a half here. So you want to test some of these values out, right? So let's start with plus minus 1. I'm going to start with f of 1. So I'm going to pretend that this guy here is f of x, right? So what I'm going to do here is I'm going to do f of 1 here, and if I plug it in, I get negative 2, 1 cubed minus 6 times 1 squared plus 12 times 1 plus 16. And this is going to give me negative 2 minus 6 plus 12 plus 16. And you can actually notice here that this is negative 8 plus 12 plus 16. This is equal to 20. Okay, so this won't work, right? So f of 1 is equal to 20, right? So there is a remainder of 20. So we're still using remainder theorem. Let's do f of negative 1 just to test it. We have negative 2, negative 1 cubed minus 6, negative 1 squared plus 12 times negative 1 plus 16, right? You get positive 2 minus 6 minus 12 plus 16, and this actually gives you 0. So f of negative 1 gives you 0. So therefore, according to factor theorem, x plus 1 is a factor. Okay, so now that we know we have one of the factors, then what we want to do is we want to find the rest of the factors. So for this case, you can either use long division or synthetic division. As long as the factor is linear, as long as the divisor is linear, as in the degree is 1 on the divisor, then you can use synthetic division. So I'm going to use synthetic division for this. So when I'm doing synthetic division, let's do that here. When I'm doing synthetic division, I'm going to write down my terms up top. This is x cubed, x squared, x to the power 1, x to the power 0. And then basically the value I plugged in to find my remainder, I'm going to use that on the outside. My coefficients here for the x cubed is negative 2. For x squared, it's negative 6. X to the power 1 is positive 12, and x to the power 0 is 16. Okay, so those are my coefficients. The first thing you want to do here is I'm going to bring down the leading coefficient, which is negative 2. So you bring down your leading coefficient. You multiply your leading coefficient with your k value, which is the negative 1. So when you multiply these two, you get positive 2. Then you add the coefficients of negative 6 plus 2, which is going to give you negative 4. Then you do negative 1 times negative 4, which is positive 4. Then you do 12 plus 4, which is 16. Then you do negative 1 times 16, which is negative 16. And when you add these two together, you get 0. Now the quotient of synthetic division, because you're dividing a cube by a linear, or degree of 1, the quotient should have the terms x squared, x to the power 1, x to the power 0, and the remainder. Okay, so this quotient here is going to look like negative 2x squared plus 4x plus 16. Okay, so what our factored expression looks like so far is x plus 1 times negative 2x squared plus 4x plus 16. You can understand that this is a quadratic expression, and we can actually factor this further. So if we factor this further, I'm going to factor out a negative 2 here. So you get x squared minus 2x minus 8. And then you want to factor this quadratic expression. So for factoring this quadratic expression, we're factoring this by decomposition, two numbers that add up to negative 2 that multiply to negative 8, right? You could do 4 and 2. So negative 4 and positive 2. So I'm going to rewrite it this way. and then factor this out. So you get x minus 4 plus 2, x minus 4, and then I'm just going to factor by grouping, right? So this is negative 2, x plus 2 times x minus 4. So our fully factored expression is x plus 1 times, I'm going to put the negative 2 on the outside, and you can write it in any order, x plus 1 times x plus 2 times x minus 4. Okay, so now that's our expression that's fully factored, except we're not done yet, right? Okay, so after we have the factored expression, I'm just going to make some space here. And next we want to figure out the intervals using this expression. So I'm going to rewrite my inequality as negative 2 x plus 1 times x plus 2 times x minus 4 is less than or equal to 0, right? And in this case, what you want to do is you want to find your critical points. Okay, so my critical points here, I'm just going to use a different color for this. My critical points here are going to be negative 1, negative 2, and 4. Okay, after you find your critical points, then what you want to do is you want to design your intervals, right? So design table of intervals. No, sorry, design, not table of intervals, design your number line to determine the intervals. Right, so we need to determine our intervals before we actually design our table of intervals. So to do that, I'm going to design my number line, which is this. And because it's less than or equal to 0, it's going to be inclusive of the critical points. So this is negative infinity. This is negative 2, negative 1, positive 4, and positive infinity. And then using my critical points, I can figure out what the intervals are. So this guy here is negative infinity and negative 2. This guy here is negative 2 and negative 1. This guy here is negative 1 and 4. And this guy here is 4 and positive infinity. So you can notice that we're using the square brackets because the points are inclusive, right? And after we design our number line and we create and we find our intervals, and you should see that there should be one more interval than critical points. If you have 3 critical points, you have 4 intervals. Then what we want to do is we want to design our interval table. So I'm just going to make some space here to design our interval table. Okay, so for designing our interval table, what we want to do is we want to place our intervals on the top. Okay, so we have 4 intervals that you want to place on top. So we have the negative infinity, negative 2, negative 2, negative 1, negative 1 and 4, and positive 4 and positive infinity. Okay, so we have our intervals on top. These x can belong to values within these intervals, and then we place our factors on these rows, right? Now the last row here is going to be our combined function f of x. Okay, so it's going to be basically the collection of all of the factors, right? So I'm going to place my factors. I'm going to include the negative 2x with the first factor, so negative 2x x times x plus 1. Then I have x plus 2 here, and then I also have x minus 4. Okay, and then I'm going to pick a value from each interval, so I'm just going to show that using a different color. Let's say between the interval of negative infinity and negative 2, I plug in x is equal to negative 3. If I plug in negative 3, you get negative 3 plus 1, which is negative 2, times negative 2, that's positive. Right, so you have to kind of test out one value for each column, and then you can figure out the signs of each interval. So in this case, for each factor. So in this case, x is equal to negative 3. You plug it into x here. Negative 3 plus 2 is negative 1, so that's a negative. Negative 3 for x minus 4 is negative 7, so that's negative. And then when you multiply all the 3 factors together, you get positive times negative, and that's going to give you positive. So this interval actually here is going to be greater than 0, right? But you want to look for values that are less than or equal to 0, right? So let's take a look at between negative 2 and negative 1. Let's say that x is equal to negative 1.5. If you plug in negative 1.5, you get 1.5, negative 1.5 plus 1, which is negative 0.5, times negative 2 is positive. When x is negative 1.5 plus 2, that's positive. Negative 1.5 minus 4 is going to give you a negative. Okay, so you have a negative times 2 positive, that's a negative. So this is going to be less than or equal to 0. It's less than or equal to 0 because if you include negative 2 or negative 1, it's equal to 0. And you keep doing this for the other two intervals. So for this guy, I'm going to pick x is equal to 0 because it's easy. 0 plus 1, positive 1 times negative 2 is negative. 0 plus 2 is positive 2, so it's positive. 0 minus 4 is negative 4, and then this adds up to a positive, right? Negative times positive. So this is greater than 0. And then for the last interval, from 4 to positive infinity, I'm going to let x equal 5. In this case, you get 5 plus 1, which is 6, times negative 2, which is negative 12, so it's negative. 5 plus 2 is 7, so it's positive, and 5 minus 4 is positive, so this is negative. So this is less than or equal to 0. And our two solutions are going to basically be this interval and this interval, right? And those are the cases where f of x will be less than 0. So therefore, x can belong to negative 2 and negative 1, as well as or union 4 and positive infinity. Okay, and if you pick any value from these two intervals, you actually see that this inequality will be true.